Imagine standing on a cliff edge at night, staring into an ocean of stars. Your eyes trace patterns written in light that traveled years, centuries, millennia just to reach your retina. Distant islands of possibility shimmering in the darkness. Picture yourself as an explorer from centuries past, gazing across uncharted waters, wondering what lies beyond the horizon. But instead of oceans, you face the cosmic sea, billions upon billions of worlds suspended in the void. You are about to discover the ultimate frontier, not just of space, but of human potential. The universe stretches nearly 100 billion light years across, yet we remain tethered to one pale blue dot, circling an ordinary star. The paradox feels almost cruel. We've mapped galaxies billions of light years away, yet we've barely left our cosmic doorstep. We can see what we cannot reach. We can dream of what we cannot touch. Look up tonight. That light from distant stars began its journey when different civilizations walked the Earth. Some photons left their stars when dinosaurs still roamed. Others departed before Earth itself had fully formed. What does it mean to be cosmic observers, yet cosmic prisoners? We evolved to cross continents, not interstellar space. Our bodies, perfectly adapted for Earth's gravity, atmosphere, and timescales, face brutal limitations when confronting the cosmic calendar. A human lifetime, perhaps 80 years if fortunate, feels substantial to us, but measured against the stars? Against galaxies that take hundreds of millions of years to complete a single rotation, our lives are cosmic eye blinks. Yet within these biological constraints, we wonder, how far could we actually go? If we dedicated one human lifetime to traveling as far as possible into the cosmos, where might we reach? The question tugs at something deeper than curiosity. It touches our ancient need to explore, to push boundaries, to discover what lies beyond. It whispers to the part of us that gazed across ancient savannas and wondered what existed over the next hill. Tonight, we journey into this gap between human aspiration and cosmic reality. We'll explore not just distances in light years, but distances measured in human heartbeats, in generations, in the brief flicker of consciousness we're granted. The numbers will astound you. The distances will humble you. The limitations will frustrate you. But something else might happen too. A shift in perspective. A new appreciation for our place in this vast, ancient universe. We'll explore how rocket technology might evolve, how close we could approach the cosmic speed limit, and what happens to time itself as we accelerate toward it. We'll discover how Einstein's relativity creates both opportunities and paradoxes. What would you sacrifice to touch the stars? A decade of your life? The chance to see Earth again? Would you trade years for light years, familiar faces for alien horizons? Some boundaries can be pushed with technology. Others remain fixed by the laws of physics themselves. Tonight, we'll discover which constraints might bend and which stand firm as cosmic absolutes. We'll meet the dreamers who first calculated these journeys, from Konstantin Tsiolkovsky, sketching rocket equations in pre-revolutionary Russia, to modern physicists mapping the energy requirements for interstellar travel. We'll witness how our cosmic horizons have expanded through history, from believing the stars were holes in a celestial sphere, to understanding they're suns like our own, to realizing they're nuclear furnaces scattered across incomprehensible distances. The question of how far we might travel contains other questions within it. What does it mean to be human when separated from Earth? What memories would you carry with you into the void? What would you hope to find? Perhaps you're listening from bed, your own journey tonight simply from wakefulness to dreams. Consider this. As you travel into sleep, your mind will cross distances that even light cannot traverse. Consciousness remains the ultimate frontier. Tonight, we'll explore the physics, engineering, biology, and psychology of human space travel. We'll calculate maximum distances, compare propulsion technologies, and confront the harsh realities of cosmic radiation and psychological isolation. We'll discover why some scientists believe the journey itself might change what it means to be human. How adaptation to space could transform our bodies and minds across generations of travelers. Chapter 2. Our cosmic potential. The question of how far humans could travel in space during a single lifetime isn't merely academic. It speaks to something fundamental about our existence, the tension between our infinite imaginations and our finite bodies. We are strange creatures, cosmic consciousness trapped in terrestrial forms. Our minds can contemplate the edge of the observable universe, and our bodies evolve to hunt on savannas and gather in forests. Each night, we look upward and see destinations we may never reach. This cosmic yearning has shaped human culture since we first gazed skyward. Ancient myths speak of heavenly realms, of journeys beyond Earth, of transcending moral limitations. Consider the emotional weight of this contradiction. We can map galaxies billions of light years away, calculating their mass, composition, and history, yet crossing even the tiny gap to our nearest neighboring star remains beyond our grasp. This is not a tale of despair, but of perspective. Understanding our place in the cosmos doesn't diminish us, it contextualizes us. Like learning the true scale of mountains or oceans, cosmic scale offers both humility and wonder. When we ask how far we might travel, we're really asking about the nature of being human. Are we forever bound to Earth? Are we planetary creatures who briefly visited our moon? Or cosmic creatures just beginning an extraordinary journey? The numbers we'll explore tonight aren't just distances, they're possibilities. Each calculation reveals something about what we might become, about futures we might create, about legacies we might leave for generations who follow us. Our relationship with distance has always defined us. Early humans migrated across continents. Polynesians navigated vast oceans by starlight. Vikings crossed the Atlantic. Each expansion required new technology and new courage. Space represents the ultimate expansion, a journey requiring not just new vessels, but new understandings of time, of human biology, perhaps even of consciousness itself. The distances involved force us to reconsider what travel means. When we speak of traveling to distant stars, we're not just describing physical movement, but the redefinition of human experience. What does lifetime mean when time dilates near light speed? What is distance when space itself expands? These questions invite us to look inward as much as outward. They ask us to examine what we value, what we would sacrifice, what we hope to discover, and what legacy we wish to leave. If we sent humans to Proxima Centauri, over 4 light years away, the journey would take decades, even with advanced propulsion. The travelers would leave behind everything familiar, everyone they love. Why would anyone choose this? The answer lies in our nature. We explore because we must, because something in us needs to know what lies beyond, because we are a species defined not just by where we are, but by where we might go. Throughout history, explorers have left safety for uncertainty, comfort for hardship, the known for the unknown. From the first humans to leave Africa to astronauts leaving Earth, explorers have always looked beyond horizons. Tonight's journey through cosmic distances offers a certain comfort too, the comfort of context, of understanding our place in something vaster than ourselves. There's peace in facing cosmic reality with clear eyes. Consider that we exist at all, that stardust formed planets, that on at least one planet, life emerged, that after billions of years of evolution, creatures arose who could contemplate their origins and their possible futures. We are the universe examining itself. We are matter that wonders about matter. We are the cosmos conscious of its own existence. This perspective doesn't make our physical limitations disappear, but it frames them differently. The real journey we're on isn't measured in light years, but in understanding. Each discovery about cosmic distances reveals something about ourselves, our ambitions, our constraints, our potential futures. What if the most important distance isn't between stars, but between what we are now and what we might become. What if the true frontier isn't physical space, but the evolution of our relationship with space? Our cosmic potential might not be defined by how far we can travel in kilometers or light years, but by how far we can expand our definition of we, by how we might create vessels that carry not just human bodies, but human culture. When we send spacecraft to distant planets, we're already sending pieces of ourselves, our technology, our questions, our hopes. Perhaps the journey outward will always be paralleled by a journey inward, toward deeper self-knowledge. Consider that light from Proxima Centauri takes over 4 years to reach us. If we observed it today, we'd see its past. If we traveled there, we'd arrive in its future. Space travel is time travel, in this sense. The universe we observe tonight is a historical document. The light from Andromeda shows us the galaxy as it was 2.5 million years ago. When we look outward, we look backward in time. This perspective grounds our exploration of cosmic distances. We're not just calculating how far we might travel, but how we relate to a universe where distance and time are inseparably linked, where our brief lives intersect with cosmic scales. Chapter 3: The Dawn of Cosmic Understanding. Humanity's journey toward understanding cosmic distances began long before telescopes or spacecraft. Ancient observers recognized patterns in the night sky, constellations that told stories and guided navigation across seas and deserts. For most of human history, the cosmos was believed to be much smaller than we know it to be today. Early civilizations imagined the stars as holes in a celestial sphere, allowing divine light to shine through from beyond. The ancient Greeks made the first serious attempts to measure cosmic distances. Around 250 BCE, Eratosthenes calculated Earth's circumference with remarkable accuracy using nothing but shadows, geometry, and clear thinking. A century later, Hipparchus estimated the moon's distance at about 30 Earth diameters, not far from the modern value. He did this by observing solar eclipses from different locations and applying geometric principles. But the stars remained immeasurable to ancient instruments. They were understood to be distant, but how distant? Without a way to detect stellar parallax, the apparent shift in a star's position when viewed from different points in Earth's orbit, astronomers could only speculate. The cosmic distance scale expanded dramatically with the invention of the telescope. In 1610, Galileo pointed his instrument skyward and discovered that the Milky Way was composed of countless individual stars, previously invisible to the naked eye. Throughout the 17th century, the solar system grew larger in human understanding. Johannes Kepler refined planetary orbits. Isaac Newton provided the physical laws explaining their motions. The cosmic clockwork began to reveal itself. Yet the stars remained mysterious points of light. In 1838, Friedrich Bessel finally measured the parallax of 61 Cygni, proving stars were not just distant, but almost incomprehensibly so, many trillions of miles from Earth. As astronomers grasped these enormous distances, a sobering reality emerged: the gap between human capability and cosmic scale. Stars were so far away that reaching them seemed impossible by any conceivable technology. The Russian schoolteacher Konstantin Tsiolkovsky changed this perspective in 1903 when he published The Exploration of Cosmic Space by Means of Reaction Devices, the first serious scientific treatment of rocketry for space travel. Tsiolkovsky's rocket equation, still fundamental to spaceflight today, quantified the relationship between a rocket's velocity, its exhaust velocity, and the ratio of its initial to final mass. It outlined the fundamental challenge of cosmic travel. His calculations showed that conventional chemical rockets would require impossible amounts of fuel for interstellar journeys. Yet he remained optimistic, writing, "Earth is the cradle of humanity, but one cannot live in a cradle forever." The early 20th century brought Einstein's theories of relativity, forever changing our understanding of space, time, and cosmic travel. Special relativity revealed the speed of light as the universe's fundamental speed limit. This cosmic speed limit, minus 299,792,458 meters per second, presented both a challenge and an opportunity for would-be star travelers. Nothing with mass could reach this speed, yet approaching it would create interesting effects. Einstein showed that as objects approach light speed, time dilates from the traveler's perspective. A hypothetical spacecraft moving at 99% light speed would experience just 1 year, while over 7 years passed on Earth. This time dilation suggested a theoretical path to the stars within a human lifetime. If a spacecraft could approach light speed, the crew might age slowly enough to reach distant destinations within their lifespans. Meanwhile, understanding of cosmic distances continued to expand. In the 1920s, Edwin Hubble proved that spiral nebulae were actually distant galaxies, vastly expanding the known universe beyond our Milky Way. Hubble's work revealed a universe of galaxies receding from us at speeds proportional to their distance, evidence of cosmic expansion. This discovery added another layer of complexity to the challenge of interstellar travel. During the Cold War, the theoretical became practical as rockets powerful enough to escape Earth's gravity were developed. In 1957, Sputnik became humanity's first artificial satellite. 4 years later, Yuri Gagarin became the first human in space. The pace of exploration accelerated. In 1969, humans walked on the moon, our first footsteps on another world. The Apollo missions represented the farthest human beings had ever traveled from Earth. Yet the moon orbits just 1.3 light seconds away. Robotic explorers pushed farther. The Pioneer and Voyager probes launched in the 1970s became the first human-made objects to visit the outer planets. Today, Voyager 1 continues into interstellar space, over 14 billion miles from home. Yet even Voyager 1, traveling at about 38,000 miles per hour, would take over 70,000 years to reach Proxima Centauri, our nearest stellar neighbor. The gap between our robotic reach and human presence in space remains vast. Throughout the late 20th century, theoretical physicists and engineers began seriously investigating advanced propulsion concepts that might enable interstellar travel within human timescales. Nuclear pulse propulsion, conceived in Project Orion, would detonate small nuclear bombs behind a spacecraft, propelling it forward on the resulting shockwaves. Calculations suggested it could reach about 10% of light speed. Fusion rockets, solar sails, antimatter engines, and ramjet concepts that would collect interstellar hydrogen as fuel. Each presented possibilities and problems. All required technologies well beyond current capabilities. Chapter 4. Mapping the Cosmic Neighborhood. Let's establish our cosmic context by examining distances within our reach, beyond our reach, and somewhere in the uncertain middle. The territory this documentary explores. Earth orbits the Sun at an average distance of 93 million miles, a measurement astronomers call 1 astronomical unit, or O. Light from the Sun reaches us in just 8 minutes and 20 seconds at this distance. Our Moon orbits approximately 238,855 miles away, close enough that Apollo astronauts could reach it in just 3 days. Radio signals, traveling at light speed, cross this distance in 1.3 seconds. This lunar distance, the farthest humans have physically traveled, represents just a tiny fraction of even our solar system. If Earth were the size of a marble, the Moon would orbit just 7.5 inches away. Mars, often considered humanity's next destination, orbits between 34 and 249 million miles from Earth, depending on the positions of both planets. At its closest approach, light takes about 3 minutes to travel between Earth and Mars. Using current chemical rocket technology, spacecraft take between 6 and 9 months to reach Mars. Human missions would face significant radiation exposure, muscle atrophy, and psychological challenges during this journey. The outer planets present even greater challenges. Jupiter orbits at an average distance of 5.2 astronomical units from the Sun, Saturn at 9.5 astronomical units, Uranus at 19.2 astronomical units, Neptune at 30.1 astronomical units. These gas giants reside in the freezing outer reaches of our system. Beyond Neptune lies the Kuiper Belt, a region of icy bodies including dwarf planet Pluto, which orbits at an average of 39 astronomical units from the Sun. Light from the Sun takes over 5 hours to reach Pluto. Farther still is the theoretical Oort cloud, extending perhaps a quarter of the way to Proxima Centauri. This vast sphere of icy objects marks the outer boundary of our solar system, up to 100,000 astronomical units from the Sun. Only beyond the Oort cloud do we finally encounter interstellar space proper, and the true challenge of cosmic distances begins. Here, we must switch to measuring in light years. The distance light travels in 1 Earth year. 1 light year equals approximately 5.88 trillion miles or 63,241 astronomical units. It's a distance so vast that our fastest spacecraft would take thousands of years to cross a single light year at current velocities. Proxima Centauri, the nearest star to our solar system, lies 4.25 light years away. The light we see from it tonight left that star in 2020. If we launched a probe today, it would arrive long after everyone reading this has passed away. The nearest potentially habitable exoplanet, Proxima Centauri b, orbits this nearby star. Discovered in 2016, this rocky world lies in the habitable zone where liquid water might exist on its surface. Extending our view, we find the Centauri system, Alpha Centauri A and B, plus Proxima, collectively forming our nearest stellar neighbors at 4.37 light-years away. These stars appear as a single point to the naked eye from Earth. Sirius, the brightest star in our night sky, lies 8.6 light-years away. Its brilliant appearance results from both its proximity and its intrinsic luminosity. It's 25 times more luminous than our Sun. The closest known black hole, designated the Unicorn, orbits a red giant star in the constellation Monoceros, approximately 1,500 light-years away. Just reaching the neighborhood of this exotic object would require technology far beyond our current capabilities. Our entire Milky Way galaxy spans approximately 100,000 light-years in diameter, containing between 100 to 400 billion stars. From our position, about 27,000 light-years from the galactic center, we've directly observed just a tiny fraction of these stars. The nearest major galaxy to our own, Andromeda, lies approximately 2.5 million light-years away. The light we see from it tonight began its journey toward Earth when our early human ancestors were first developing stone tools. These cosmic distances present the fundamental challenge we're exploring. Human lifespans typically range from 70 to 90 years. While interstellar distances are measured in years, it takes light, the fastest thing in the universe, to travel. If we somehow develop spacecraft capable of traveling at 10% the speed of light, about 18,600 miles per second, reaching Proxima Centauri would still require over 40 years. Alpha Centauri would take nearly 44 years. At just 1% of light speed, still far beyond current technology, these journeys would extend to 425 years and 437 years respectively, requiring multiple generations to complete the journey. Our fastest current spacecraft, NASA's Parker Solar Probe, will eventually reach speeds of about 430,000 miles per hour, 0.064% of light speed, in its close approaches to the Sun. At this speed, reaching Proxima Centauri would take about 6,700 years. The cosmic speed limit isn't just technological, it's built into physics itself. As objects with mass approach light speed, They require exponentially more energy to accelerate further. Reaching 100% of light speed would require infinite energy. However, Einstein's special relativity offers an intriguing loophole for human travelers. Time dilation causes time to pass more slowly for objects moving at high velocities relative to an observer. At 90% of light speed, a spaceship would reach Proxima Centauri in 4.72 years of Earth time. But for the astronauts on board, only 2.06 years would pass due to time dilation. Their biological aging would slow relative to Earth. At 99% of light speed, the effect becomes even more pronounced. The journey would take 4.29 Earth years, but the astronauts would experience just 7.2 months. The closer to light speed, the greater this effect. This relativistic effect creates a theoretical path to the stars within a human lifetime, at least for the travelers. A spacecraft moving at 99.9% of light speed could reach the center of our Milky Way galaxy minus 27,000 light-years away, while the crew aged only 1,200 years. Of course, such velocities present enormous challenges. The energy requirements are staggering. Interstellar dust becomes deadly at such speeds. And the social implications of time dilation, returning to an Earth centuries or millennia in the future, are profound. As we move into our exploration of possible technologies and human impacts, one question emerges. Does the path to the stars lie in pushing the boundaries of physics, or in reimagining what it means to be human? Chapter 5. The Speed Paradox. The fundamental tension in interstellar travel emerges from a simple but profound contradiction: human longevity versus cosmic vastness. Our lifespans evolved for Earth-based challenges, not for crossing gulfs between stars that take light itself years to traverse. Let's explore a stunning contradiction. The faster we travel through space, the slower we move through time. This isn't science fiction, it's a direct consequence of Einstein's special relativity, confirmed by countless experiments over the past century. Time dilation creates a fascinating possibility. A spacecraft approaching light speed might enable human travelers to reach destinations thousands of light-years away within their subjective lifetimes, while centuries or millennia pass on Earth. Consider the relativistic rocket equation, which accounts for the effects of special relativity on space travel. Unlike the classical rocket equation developed by Tsiolkovsky, this version incorporates the relationship between velocity, mass, and the passage of time. At 90% of light speed, a journey to Alpha Centauri would take about 4.8 years from Earth's perspective. But the astronauts on board would experience only 2.1 years due to time dilation. Their clocks, biological and mechanical, would literally run slower. At 99% of light speed, the effect becomes more pronounced. The journey would take 4.4 years for observers on Earth, but only 7 months for the travelers. The closer to light speed, the greater this temporal divergence. This creates what philosophers call the twin paradox. If one twin stays on Earth while another travels to Alpha Centauri at relativistic speeds, the traveling twin would return younger than the Earthbound sibling, having experienced less subjective time. The contradiction becomes clear. Interstellar journeys within a human lifetime are theoretically possible, but at a profound cost. The travelers would be separated from Earth not just by distance, but by time itself. Returning from a relativistic journey, astronauts might find centuries or millennia had passed on Earth. Everyone they knew would be long dead. Human civilization itself might have transformed beyond recognition or disappeared entirely. This temporal gulf represents perhaps the greatest psychological barrier to human interstellar travel. Would anyone choose to embark on a journey that separates them forever from their own time? From everyone and everything they've ever known? Another contradiction emerges when we consider the energy requirements for relativistic travel. The closer a massive object approaches light speed, the more energy is required for additional acceleration. asymptotically approaching infinity as velocity nears light speed. This creates a practical limit long before the theoretical one. Accelerating a 100-ton spacecraft to 90% of light speed would require approximately 1,021 joules, equivalent to the entire energy consumption of human civilization for about 500 years. Some theorists propose using interstellar hydrogen as fuel via Bussard ramjet concepts, essentially refueling from the very medium through which the ship travels. But interstellar space contains only 1 to 2 hydrogen atoms per cubic centimeter on average. The contradiction here lies in physics itself, the very laws that make interstellar travel theoretically possible within a human lifetime also make it practically impossible with any technology we can currently envision. Yet another paradox emerges when we consider protection from interstellar medium. At relativistic speeds, ordinary hydrogen atoms would strike the spacecraft with energy equivalent to cosmic rays or even nuclear particles. At 99% of light speed, impact with a single gram of hydrogen distributed across the flight path would release energy equivalent to about 3 kilotons of TNT. Even single atoms would become dangerous projectiles at such velocities. This creates a technological contradiction. The speeds required for practical interstellar travel within human lifetimes would turn the near vacuum of space into a dangerous radiation environment requiring massive shielding, which would increase the craft's mass. The increased mass would require more energy for acceleration, which would require more fuel, which would add more mass. This cascade of requirements creates what engineers call a tyranny of the rocket equation on steroids. What about suspended animation or hibernation technologies? If humans could be placed in biostasis for decades or centuries, perhaps we could travel at more modest speeds while subjectively experiencing the journey as brief. Current cryonics techniques can preserve biological tissue, but not in a way that allows revival with current technology. Even if perfected, such techniques would merely sidestep rather than solve the time versus distance problem. Another approach considers generational ships, enormous vessels where multiple generations would live and die during centuries-long journeys between stars. The passengers who arrive would be the distant descendants of those who departed. This approach avoids relativistic speeds but introduces new contradictions. How would a closed human society evolve over centuries of isolation? Would later generations maintain commitment to the original mission? Would they even want to disembark upon arrival? Some theorists propose uploading human consciousness to artificial substrates, essentially becoming software that could experience subjective centuries in moments of objective time, or simply shut down during transit and reactivate at the destination. This approach represents perhaps the most radical reimagining of what human travel might mean. Would digitized minds be the same people who were scanned? Would such entities still be human in any meaningful sense? The contradictions multiply when we consider communication. Even if humans could reach Alpha Centauri within a subjective decade, any message back to Earth would take 4.37 years to arrive, traveling at light speed. Real-time communication across interstellar distances is impossible under our current understanding of physics. Any human expedition would be effectively cut off from Earth guidance or instructions once they departed the solar system. What about exotic physics? Theoretical concepts like the Alcubierre warp drive propose cheating the light speed limit by contracting space in front of a vessel while expanding it behind, effectively moving the space around the ship. Such concepts require exotic matter with negative energy density, something that may be physically impossible and would need quantities of energy equivalent to converting the mass of Jupiter entirely to energy. The contradiction remains. Some physicists propose exploiting quantum entanglement for faster-than-light communication, but current understanding suggests this violates causality. Entangled particles exhibit correlated properties but cannot be used to transmit information faster than light. Each potential solution to interstellar travel seems to introduce new contradictions or require physics beyond our current understanding. The dream of reaching the stars within a human lifetime remains caught between theoretical possibility and practical impossibility. This fundamental tension between cosmic scales and human scales shapes every aspect of our relationship with space. We can see farther than we can reach. We can imagine journeys we cannot undertake. We can calculate distances we cannot cross. Yet even these contradictions reveal something profound about human nature. Throughout history, we've encountered seemingly insurmountable barriers, only to eventually find ways through, around, or over them. The stars may be no different. Perhaps the most profound contradiction is this: the very intelligence that allows us to comprehend cosmic distances also drives us to overcome them. We calculate the immense gulfs between stars precisely because we dream of crossing them. Chapter 6: Cosmic Misconceptions. Popular culture has given us many compelling but misleading images of interstellar travel. From Star Wars to Star Trek, science fiction often depicts journeys between distant star systems as taking hours or days rather than decades or centuries. These fictional universes typically include technologies that circumvent the light speed limit: hyperdrives, warp engines, jump gates, or wormholes. While entertaining, these create misconceptions about what's physically possible under the laws of physics as we understand them. Perhaps the most common myth is that we'll soon develop technology to jump or warp between stars, making cosmic distances irrelevant. These concepts remain firmly in the realm of speculation, with no experimental evidence supporting their possibility. Another widespread misconception involves misunderstanding the cosmic speed limit. The speed of light isn't just a current technical limitation we'll eventually engineer past. It appears to be a fundamental property of spacetime itself. According to special relativity, as an object with mass approaches light speed, its relativistic mass increases toward infinity. Accelerating to exactly light speed would require infinite energy, a physical impossibility for any object with rest mass. Some popular accounts suggest that quantum entanglement might enable faster-than-light communication or quantum teleportation of humans between stars. This fundamentally misunderstands what entanglement actually allows. While entangled particles do exhibit correlated properties instantaneously across distances, this correlation cannot be used to transmit information faster than light. The no communication theorem in quantum mechanics explicitly prohibits this. Similarly, quantum teleportation doesn't actually teleport matter. It transfers quantum states between particles using both quantum and classical communication channels. The classical channel is still limited to light speed, preventing faster-than-light information transfer. Another common misconception involves black holes as potential shortcuts through space. While theoretical physics suggests the possibility of traversable wormholes connecting distant points in spacetime, maintaining such shortcuts would require exotic negative energy. Current physics provides no known mechanism for producing the necessary quantities of negative energy, and most theoretical physicists consider traversable wormholes highly speculative at best, physically impossible at worst. Some viral social media posts have suggested that NASA or other agencies are developing warp drives based on the theoretical work of physicist Miguel Alcubierre. While the mathematics of such drives are interesting, practical implementation faces insurmountable challenges. The original Alcubierre drive concept would require more energy than exists in the observable universe. Later refinements reduced this to merely the mass energy of Jupiter, still far beyond any conceivable engineering capability. Another persistent myth suggests that classified government programs have already achieved breakthrough propulsion technologies. If such technologies existed, they would require new physics that somehow remains hidden from the global scientific community. Science advances through peer review and reproducible results. Major physics breakthroughs can't remain hidden for long, as they would be discovered independently by researchers worldwide working from the same fundamental principles. Some popular accounts mistakenly suggest that ion drives or nuclear propulsion could approach light speed. While these technologies offer improvements over chemical rockets, they still fall far short of the velocities needed for practical interstellar travel. The most efficient ion thrusters achieve exhaust velocities around 50 kilometers per second, impressive compared to chemical rockets, but still just 0.017% of light speed. Nuclear propulsion might reach 3 to 5% of light speed with theoretical designs. Another misconception involves antimatter propulsion. While antimatter offers the highest energy density of any known fuel, the total worldwide production of antimatter is currently measured in nanograms at a cost of billions of dollars per gram. Even if production improved dramatically, antimatter propulsion would face enormous engineering challenges in containing and directing the energy from matter-antimatter annihilation, which releases radiation in all directions rather than as directed thrust. Some futurists promote solar sails pushed by powerful lasers as a path to the stars. While theoretically possible, the infrastructure required would be staggering. Laser arrays with power measured in terawatts focused over interstellar distances. The Breakthrough Starshot initiative proposes using this approach to send gram-sized probes to Alpha Centauri at 20% of light speed. Even this limited goal would require the largest engineering project in human history. A common misunderstanding involves conflating robot probes with human missions. While we might send small, unmanned probes to nearby stars within a few decades, human missions face vastly greater challenges of life support, radiation protection, and psychological factors. Some popular sources suggest cryonic suspension as a near-term solution for interstellar travel. However, current technology can't reversibly preserve human brain structure, and even theoretical future techniques would face enormous engineering and biological challenges. Another widespread myth suggests that generation ships represent a straightforward, near-term alternative to faster-than-light travel. While physically possible, such vessels would require self-sustaining ecosystems functioning flawlessly for centuries. The psychological, sociological, and governance challenges of a generation ship would be enormous. How would people born on such a vessel, who never chose the journey, maintain commitment to a mission they didn't initiate? Science communicators sometimes inadvertently foster misconceptions by using analogies that oversimplify cosmic distances. Comparing the solar system to everyday objects can help comprehension, but may unintentionally diminish the true scale of interstellar space. If Earth were the size of a marble, the Sun would be a ball about 7.5 feet in diameter, located 785 feet away. On this scale, Proxima Centauri would be another 7-foot ball located 31,000 miles away, more than once around Earth's equator. Some enthusiasts misinterpret the Fermi paradox, the apparent contradiction between high probability of extraterrestrial civilizations and our lack of contact with them, as evidence that interstellar travel must be easy, just undiscovered by humans. A more sobering interpretation is that the physics of interstellar travel represents a genuine barrier that even advanced civilizations cannot easily overcome. The vast distances between stars may fundamentally limit physical contact between civilizations. Another misconception involves underestimating the dangers of interstellar space. Beyond our solar system's protective heliosphere, cosmic radiation increases significantly. At relativistic speeds, even the sparse atoms of interstellar hydrogen become dangerous. Popular accounts rarely mention that interstellar travelers would face constant micrometeoroid impacts. At relativistic speeds, even tiny particles carry enormous kinetic energy. A grain of sand could impact with the force of a bomb. Some enthusiasts suggest space-based habitats as proving grounds for generation ship technology. While O'Neill cylinders or similar structures might sustain closed ecosystems, they would still receive maintenance, resources, and psychological support from Earth. A related myth suggests that terraforming Mars or settling space habitats would prepare us for interstellar colonization. While valuable for expanding human presence, these projects face fundamentally different challenges than interstellar voyages. Perhaps the most dangerous misconception is that technology alone will solve the interstellar challenge. While advances in propulsion, materials, computing, and biology will help, the fundamental constraints of physics, energy, and human psychology remain. The sobering truth is that human interstellar travel remains one of the hardest problems we've ever contemplated. Not because we lack imagination or determination, but because the universe itself seems structured to make such journeys extraordinarily difficult. Chapter 7. What changes if we go interstellar? What's truly at stake in the question of human interstellar travel? Beyond scientific curiosity, the answer shapes our understanding of humanity's future, our cosmic significance, and perhaps even the meaning we find in our brief lives. If we could travel significant distances within a human lifetime, our relationship with time itself would fundamentally change. The relativistic effects would create divergent timelines. Travelers would experience different histories than those they left behind. Imagine departing Earth for Barnard's star, 6 light-years away, at 99% of light speed. You would experience the journey as taking just 10 months, while on Earth, 6 years would pass. Your personal timeline would permanently desynchronize from Earth's. The social implications are profound. Would interstellar travelers form a distinct class of humans, experiencing time at different rates? Would they become a bridge between different eras of human civilization, carrying culture across not just space but time? If we developed relativistic travel technology, would we fracture into multiple human timelines? Some might live in the fast lane of Earth time, while others experience subjective centuries and what would be mere decades for stay-at-home humans. This capability would fundamentally change our concept of human history. Instead of a single timeline, we might develop a complex web of subjective histories. Astronauts returning from distant journeys would be living time, capsules of earlier cultural eras. Our relationship with mortality might also transform. If suspended animation became possible, humans might choose to experience only selected portions of future history, effectively skipping ahead to eras of particular interest or importance. The practical stakes extend beyond philosophy. Interstellar capabilities would fundamentally alter human civilization's resilience. With self-sustaining colonies around multiple star systems, humanity would become immune to extinction from planetary or even solar system-wide catastrophes. This cosmic insurance policy represents perhaps the strongest practical argument for pursuing interstellar travel, despite its difficulties. A multistellar civilization could survive disasters that would extinguish a single planet or single star species. The challenges of interstellar travel are driving innovations in multiple fields today. Research into closed-loop life support systems, radiation protection, and long-duration spaceflight psychology will benefit humans on Earth regardless of whether we reach the stars. Advanced propulsion research leads to breakthroughs in plasma physics, material science, and energy generation. The pursuit of fusion for spacecraft propulsion could help solve Earth's energy challenges, even if no starship ever launches. If we discovered a breakthrough enabling practical interstellar travel, every aspect of human civilization would transform. Energy would become essentially unlimited. Material scarcity would end as resources from multiple star systems became accessible. The economics of such capability would reshape society. When energy costs approach zero and resources become effectively infinite, what happens to economic systems based on scarcity? What new forms of wealth and value might emerge? The environmental implications are equally profound. Abundant clean energy and access to off-Earth resources could end destructive extraction practices on Earth. Our home planet might transition from an exploited resource to a preserved garden. The philosophical stakes may be even higher. If humans can reach other stars, we would gain direct evidence about the prevalence of life in the universe. Are habitable worlds common or rare? Does life emerge wherever conditions permit? Most profound of all, are we alone? The distances between stars have thus far prevented us from answering humanity's oldest question. If we could cross those gulfs, we might finally discover whether other intelligences share our universe. The answer would transform human self-understanding regardless of outcome. Finding ourselves alone in the cosmic neighborhood would suggest intelligence might be vanishingly rare, placing special responsibility on humanity as conscious stewards of life. Discovering other civilizations would be equally transformative. Contact with independently evolved intelligence would provide perspective on which aspects of human nature are universal consequences of intelligence and which are accidents of our particular evolution. The absence of clear evidence for interstellar civilizations, the famous Fermi paradox, might itself tell us something profound. Perhaps interstellar travel is simply too difficult for any civilization, imposing a natural limit on cosmic expansion. Alternatively, perhaps civilizations capable of interstellar travel universally choose not to use that capability for physical expansion. They might focus inward on virtual realms or consciousness exploration instead of outward on cosmic colonization. This possibility suggests interstellar travel might be technically feasible but culturally irrelevant to advanced civilizations, a sobering thought for those who see cosmic expansion as humanity's destiny. The timescales of interstellar travel also force us to confront questions about cultural continuity. What aspects of human culture would survive centuries-long journeys? What would be preserved? What would be lost? What would transform beyond recognition? Generation ships would become civilizations unto themselves, with their own histories, cultures, and possibly languages evolving during the journey. The descendants who arrived might share little with the ancestors who departed. Even with relativistic travel, the one-way nature of time dilation means travelers could never return to the era they left. Every interstellar journey would be, in some sense, a one-way trip to the future. This asymmetry raises questions about human connection. Would interstellar travelers maintain meaningful bonds with Earth culture as it evolved during their absence? Or would they become effectively separate branches of humanity? The technical challenges of interstellar travel are forcing us to reconsider what it means to be human. If biological humans cannot practically cross interstellar distances, would post-biological alternatives, uploaded minds, artificial intelligence, or human-machine hybrids, still constitute human exploration? If we sent human genetic material to be gestated at the destination, rather than living humans making the journey, would we consider the resulting colony truly human? These questions probe the boundaries of human identity itself. The pursuit of interstellar travel capabilities, whether successful or not, expands our perspective on cosmic timescales. Planning missions that would take centuries focuses our attention on multi-generational thinking in ways few other human activities can match. Such expanded time horizons might influence our approach to challenges like climate change, biodiversity loss, and sustainable development. The mindset required for interstellar planning naturally aligns with long-term stewardship of Earth. From a scientific perspective, interstellar capabilities would revolutionize astronomy and cosmology. Direct measurements at multiple locations light-years apart would provide unprecedented data about stellar processes, cosmic action, and fundamental physics. The pursuit also drives technological innovation in unexpected ways. Research on radiation shielding for interstellar travelers could lead to better cancer treatments. Work on closed ecological systems could improve sustainable agriculture on Earth. Perhaps most profoundly, the question of interstellar travel challenges us to define what we value most about being human. Is physical presence essential to human experience? Or could we achieve meaningful exploration through robotic proxies? If we developed artificial general intelligence, would sending AI representatives to other stars constitute human exploration by proxy? Or would it represent the passing of the torch to our technological descendants? If we discover that human interstellar travel remains forever impractical, we face an existential question. Can we find meaning and purpose within the cosmic boundaries physics imposes? Can we be content as a one-star species? Alternatively, if we eventually develop true interstellar capabilities, we would confront a different question. What kind of cosmic citizens should we be? What ethical principles should guide human expansion into a universe that has developed for billions of years without us? These questions lead us to perhaps the deepest implication of interstellar travel. It would require us to develop a cosmic ethics, principles for human behavior on universal scales of space, time, and possibly interaction with other forms of life. Whatever we discover about the practical limits of human travel, the pursuit itself reveals something profound about our species. We are creatures who evolved on the savannas of a single planet, yet dared to contemplate journeys between the stars. This paradox between our biological limitations and our limitless aspirations may ultimately be what defines us. Whether we physically reach the stars or not, the yearning itself shapes who we are and who we might become. As we prepare to explore the most radical possibilities and ultimate limits in our final act, one question emerges: what price would we pay to touch the stars? And would that price, in time, in transformation, in transcending our current form, still constitute a human journey? Chapter 8: Pathways to the Stars. As we explore the outer boundaries of human potential for space travel, three primary theoretical pathways emerge. Each represents a different approach to the fundamental challenge of crossing interstellar distances within a human lifetime. The first pathway focuses on pushing conventional physics to its limits, developing propulsion systems that could approach significant fractions of light speed without requiring new physical laws or exotic matter. The second pathway explores how we might modify the human element of the equation, extending lifespans, adapting biology, or transforming consciousness to match the vast timescales of interstellar journeys. The third pathway investigates theoretical physics beyond our current understanding, searching for loopholes in relativistic limitations or entirely new principles that might revolutionize our concept of space travel. Let's examine the first pathway, approaching light speed through advanced propulsion. Several theoretical propulsion systems might enable velocities between 10 to 50% of light speed, sufficient for interstellar journeys within decades rather than centuries. Nuclear pulse propulsion, first conceived in Project Orion, would use the energy of nuclear explosions directed against a massive pusher plate. Calculations suggest this approach could theoretically achieve 3 to 5% of light speed. The technical challenges include developing materials that could withstand repeated nuclear explosions, radiation containment for the crew, and the political hurdles of launching thousands of nuclear devices into space. Fusion rockets represent another promising approach. By harnessing the same process that powers stars, these engines could potentially achieve exhaust velocities up to 10% of light speed, enabling journeys to nearby stars within decades. The British Interplanetary Society's Project Daedalus, designed in the 1970s, proposed using deuterium-helium-3 fusion to propel a robotic probe to Barnard's star. The conceptual spacecraft would have achieved about 12% of light speed. Current fusion research focuses primarily on energy production rather than propulsion, but principles developed for terrestrial fusion reactors could eventually be adapted for spacecraft engines once the technology matures. Antimatter engines represent the theoretical peak of conventional propulsion. Matter-antimatter annihilation converts mass to energy with perfect efficiency, according to Einstein's E equals mc equation. far more efficient than chemical or even nuclear reactions. A spacecraft powered by antimatter annihilation could theoretically reach 50 to 70% of light speed, making journeys to nearby stars possible within a human lifetime, especially when combined with the time dilation effects at such velocities. The challenges are formidable. Current antimatter production rates are measured in nanograms per year at facilities like CERN, at costs of billions of dollars per gram. Even if production improved dramatically, containment presents enormous technical difficulties. Despite these challenges, antimatter-catalyzed fusion or antimatter-initiated fission might provide intermediate solutions, using tiny amounts of antimatter to trigger more conventional nuclear reactions, potentially achieving velocities of 10 to 20% of light speed. Turning to our second pathway, modifying the human element, several approaches might make interstellar journeys compatible with human timescales without requiring near-light speed travel. Radical life extension represents one approach. If human lifespans could be extended to several centuries through biological or technological means, journeys that take decades or even centuries would become feasible within a single lifetime. Research into the biology of aging has identified several promising avenues, from telomere maintenance to cellular repair mechanisms. Some researchers suggest the first humans who might live to 150 or beyond may already have been born. Biostasis, often called suspended animation or hibernation, offers another approach. By dramatically slowing metabolic processes, travelers might experience subjective journey times far shorter than the objective duration. Unlike science fiction depictions of freezing travelers, realistic approaches focus on induced torpor states similar to those seen in hibernating animals, potentially combined with medical techniques to preserve tissue at low temperatures. The most radical approach involves mind uploading, transferring human consciousness to artificial substrates. Digital minds could experience subjective centuries and moments of objective time, or simply shut down during transit and reactivate at the destination. This approach raises profound philosophical questions about identity and continuity of consciousness. Would the uploaded mind truly be the same person? Would such an entity still represent human exploration in any meaningful sense? The third pathway explores theoretical physics beyond current understanding, searching for possibilities that might circumvent rather than overcome the light speed barrier. Wormholes represent one such possibility. Theoretical tunnels through space-time that could connect distant points, potentially allowing travel between them without crossing the intervening space. Einstein's equations permit such structures, but they would require exotic matter with negative energy density to remain open. Whether such matter can exist in sufficient quantities remains highly speculative. The Alcubierre warp drive represents another theoretical approach. Rather than moving through space faster than light, it would contract space ahead of the vessel while expanding it behind, effectively moving a bubble of spacetime. Like wormholes, the original concept required enormous quantities of exotic negative energy. Recent theoretical refinements have reduced the energy requirements, but they remain far beyond any conceivable engineering capability. Quantum entanglement has sometimes been suggested as a basis for instantaneous communication or even transportation across interstellar distances. However, the no communication theorem in quantum mechanics explicitly prohibits using entanglement to transmit information faster than light. Examining these pathways realistically, the near-term prospects for human interstellar travel within a single lifetime appear limited. The first pathway, advanced propulsion, offers the most promising near-term approach, but would still require massive technological leaps. A fusion-powered spacecraft might feasibly reach 10 to 15% of light speed within the next century, allowing journeys to the nearest stars in 30 to 40 years. Combined with modest life extension or limited biostasis, this could bring interstellar travel within a human lifetime. The second pathway, modifying humans raises profound ethical and philosophical questions. How much can we change the human traveler before the journey ceases to be human exploration? Is a digital copy of consciousness still the original person? The third pathway, exotic physics, remains highly speculative. While we should never discount the possibility of revolutionary discoveries, planning for interstellar travel based on physics beyond our current understanding represents a high-risk strategy. Given these considerations, a hybrid approach may offer the most practical path forward, combining advances in propulsion technology with modest biological modifications, and accepting that the first human interstellar journeys will likely take decades rather than years. Such hybrid journeys might involve small crews in rotating habitats, spending 30 to 40 years in transit to nearby stars, utilizing limited hibernation during the middle portion of the journey, and relying on closed ecosystem life support systems. The technical challenges remain enormous, but unlike faster-than-light travel, they violate no known laws of physics. With sufficient resources and determination, humanity could likely embark on such journeys within the next few centuries. Perhaps the most important insight from this analysis is that interstellar travel within a human lifetime remains theoretically possible without requiring new physics, just extraordinarily difficult engineering, sustainable closed ecosystems, and a reimagining of what space exploration means. Chapter 9. The Emerging Picture. Recent advances in observational astronomy, propulsion technology, and our understanding of human biology are reshaping our view of the interstellar travel challenge. New instruments are revealing both opportunities and obstacles on our potential path to the stars. The James Webb Space Telescope, launched in 2021, represents a quantum leap in our ability to characterize potentially habitable exoplanets. Its infrared capabilities allow scientists to analyze the atmospheric composition of distant worlds, searching for biosignatures. This capability transforms the interstellar travel equation by allowing us to better identify promising destinations before launching multi-generational missions. Rather than traveling blind, future explorers could target worlds with conditions suitable for human settlement. The Extremely Large Telescope, ELT, expected to begin operations in 2028, will further enhance our exoplanet detection capabilities. With a 39-meter primary mirror, it will collect enough light to directly image some nearby Earth-like planets. These observational advances address a critical question. Are their destinations worth the enormous cost and effort of interstellar travel? Preliminary data suggests potentially habitable worlds exist around many nearby stars, but detailed characterization remains ongoing. Beyond identifying destinations, recent advances in gravitational wave astronomy have opened entirely new windows into fundamental physics. The detection of gravitational waves by LIGO in 2015 confirmed a century-old prediction from Einstein's general relativity. This growing field may eventually reveal phenomena or principles that could transform our understanding of spacetime itself. While speculative, breakthroughs in this area could potentially identify new approaches to the interstellar travel challenge. On the propulsion front, small-scale demonstrations of light sails have proven the basic principle of radiation pressure propulsion. The Planetary Society's LightSail 2, launched in 2019, successfully demonstrated controlled solar sailing in Earth orbit. Scaling this technology, the Breakthrough Starshot initiative proposes using ground-based laser arrays to accelerate gram-scale probes to 20% of light speed, potentially reaching Alpha Centauri within 20 years of launch. While these starships would be far too small to carry human passengers, they could serve as pathfinders, transmitting detailed data about nearby star systems and validating the laser sail propulsion concept at interstellar scales. Recent research into fusion propulsion has also shown promise. The direct fusion drive concept under development at Princeton, plasma physics, Laboratory could potentially achieve specific impulses 10 times greater than chemical rockets while producing both thrust and electricity. In the biological domain, advances in understanding the mechanisms of aging have opened potential pathways to modest life extension. Researchers have identified cellular processes that could potentially extend human lifespans to 120 to 150 years with sufficient technological development. Even this moderate extension would significantly impact the interstellar travel equation. A mission launched at 10% of light speed with travelers whose biological clocks could be slowed by 50%, could reach stars up to 15 light-years away within a subjective lifetime. Neuroscience is also advancing our understanding of consciousness, memory, and the biological basis of subjective time perception. Some research suggests that subjective time perception might be modifiable, potentially making long-duration space missions subjectively shorter. Artificial intelligence and robotics advances are reshaping the human-machine relationship in ways that could transform interstellar exploration. Rather than an either-or choice between human or robotic missions, future expeditions might involve deeply integrated human-machine systems. Advanced AI systems could handle spacecraft operations during decades-long transits, with humans remaining in biostasis during the journey. The AI wouldn't replace human explorers, but would serve as their extension during periods when biology requires suspension. Meanwhile, materials science breakthroughs are addressing one of the most significant challenges for long-duration spacecraft: radiation shielding. New composite materials and electromagnetic shielding concepts could potentially provide protection without prohibitive mass penalties. These technological advances must be considered alongside emerging theoretical paradoxes that complicate our understanding of interstellar travel. One such paradox involves the sustainability of multi-generational missions. Computer simulations of closed human populations suggest that maintaining genetic diversity over centuries-long journeys would require either large, initial populations, thousands of individuals, or advanced reproductive technologies to preserve genetic diversity from a smaller crew. This creates a paradox of scale. Larger populations require larger spacecraft with greater resource requirements, while smaller crews face genetic bottleneck issues that could threaten the mission's long-term viability. Another emerging paradox involves the relationship between technology advancement and mission planning. If we launch a multi-generational starship using current or near-future technology, it may be overtaken during transit by later missions using more advanced propulsion. This weight calculation suggests that immediate departure with slower technology might result in later arrival than waiting for propulsion breakthroughs. Yet waiting indefinitely for perfect technology means never departing at all. New understanding of stellar evolution adds another layer to our interstellar calculations. Recent observations confirm that potentially habitable exoplanets around red dwarf stars, the most common stellar type, may face extreme radiation environments challenging to human settlement. This narrows the list of viable destination systems, potentially increasing travel distances to reach truly habitable worlds. Stars like our Sun, G-type main sequence stars, represent only about 7.5% of stars in our galaxy. The emerging observational data also complicates the Fermi paradox. If interstellar travel is feasible for advanced civilizations and habitable worlds are common, the absence of obvious evidence for cosmic travelers raises profound questions about the rarity of technological intelligence. One resolution to this paradox suggests that the challenges of interstellar travel are simply too great for any civilization to overcome at scale. Our emerging understanding of the energy requirements and engineering challenges lends some credence to this perspective. However, recent advances in observational techniques have just begun to search for evidence of extraterrestrial technology. The Galileo project, launched in 2021, specifically aims to search for evidence of extraterrestrial artifacts using modern astronomical techniques. Another paradox emerges from the relationship between subjective and objective time during relativistic travel. A crew traveling at high percentages of light speed would experience time dilation. Their subjective experience of the journey would be shorter than Earth time. This creates a temporal disconnection. Upon arrival at a destination 25 light-years away after traveling at 99% of light speed, only about 3.5 years would have passed for the crew, but they would arrive 25 years in Earth's future. Any return journey would compound this effect. A round trip would place the travelers 50 years in Earth's future, while aging only about 7 years themselves. The travelers would become temporal explorers as much as spatial ones. This temporal aspect of interstellar travel receives less attention than the spatial challenges, yet it represents perhaps the most profound transformation of human experience that such journeys would entail. Recent theoretical work has explored the possibility of quantum gravity effects at extremely high energies. While highly speculative, some models suggest that the apparent light speed barrier might not be absolute at the quantum level. These theories remain far from experimental verification, but they highlight how incomplete our understanding of physics at extreme scales might be. The history of science suggests caution in declaring any current understanding final. When we integrate these emerging observations, technologies, and paradoxes, a complex picture emerges. Interstellar travel within a human lifetime remains at the very edge of theoretical possibility, neither clearly impossible nor obviously achievable. This uncertainty itself is significant. Throughout history, many once impossible dreams have become reality, while others have remained firmly beyond reach. The question of human interstellar travel appears to sit precisely on this boundary. Chapter 10: The Cosmic Human Journey. After exploring the physics, biology, technology, and philosophy of interstellar travel, we return to our central question: how far could humans actually travel through space in one lifetime? The answer contains multiple layers, each revealing something profound about both the universe and ourselves. Let's begin with the most straightforward assessment based on our current understanding of physics and technology. Without invoking speculative physics beyond Einstein's relativity, the maximum distance humans could physically travel in a typical 80-year lifespan depends primarily on three factors: achievable velocity, time dilation effects, and biological considerations. With current chemical rocket technology, the practical limit for human exploration remains within our solar system. Voyager 1, our fastest outbound spacecraft, would take about 80,000 years to reach Proxima Centauri at its current velocity of 17 kilometers per second. Nuclear thermal propulsion, potentially achievable within the next few decades, might increase spacecraft velocities to 30 to 50 kilometers per second. This would reduce travel time to Proxima Centauri to roughly 25,000 to 40,000 years, still far beyond a human lifetime. More advanced concepts like fusion propulsion could theoretically achieve 1 to 5% of light speed, reducing travel time to our nearest stellar neighbor to 85 to 425 years. While a significant improvement, this remains beyond a single human lifespan. The picture changes dramatically when we consider velocities approaching significant fractions of light speed. At 50% of light speed, a journey to Proxima Centauri would take about 8.5 years from Earth's perspective. More importantly, at this velocity, time dilation effects become significant. The travelers would experience only about 7.4 years due to relativistic time dilation, potentially bringing the journey within a human lifetime. At 90% of light speed, the effects become more pronounced. The journey to Proxima Centauri would take 4.7 years from Earth's perspective, but only 2.1 years for the travelers. Time dilation has effectively compressed space for the crew. This effect increases dramatically as velocity approaches light speed. At 99% of light speed, travelers would experience just 7 months during a journey that takes 4.3 years from Earth's perspective. These relativistic effects create a theoretical window for human interstellar travel within a subjective lifetime. At velocities above 90% of light speed, travelers could potentially reach stars up to 4050 light-years away while aging only 40 to 50 years subjectively. This sphere encompasses approximately 2,000 star systems, including well-known stars like Vega, 25 Li, Fomalhaut, 25 Li, and Altair, 17 Li. Many of these systems likely contain potentially habitable worlds. However, the engineering challenges of achieving such velocities are enormous. The energy required to accelerate a 1,000-ton spacecraft at 99% of light speed exceeds the annual energy consumption of human civilization by several orders of magnitude. Additionally, interstellar dust and gas, which average just 1 atom per cubic centimeter, become dangerous radiation sources at relativistic speeds. Effective shielding would add significant mass to any interstellar vehicle, further increasing energy requirements. When we consider these practical limitations, a more realistic assessment might focus on velocities between 10 to 50% of light speed, potentially achievable with advanced antimatter catalyzed fusion or similar technology centuries from now. At these velocities, the maximum practical distance for a human lifespan of 80 years, accounting for acceleration, deceleration, and modest time dilation, would be approximately 10 to 30 light-years, encompassing approximately 50 to 500 star systems. This more conservative estimate still includes promising destinations like Tau Ceti, 11.9 Li, which is known to host potentially habitable exoplanets, and Epsilon Eridani, 10.5 Li, a young solar-type star where planets are still forming. But physics and engineering tell only part of the story. The psychological and biological aspects of long-duration space travel introduce additional constraints that may prove as limiting as propulsion technology. Studies of isolated crews in Antarctic research stations and space analog environments suggest that maintaining psychological health during decade-long missions presents enormous challenges. Social dynamics, confinement, and separation from Earth all take a toll. The biological impacts of long-duration spaceflight, muscle atrophy, bone density loss, radiation exposure, and immune system changes add another layer of constraints. A realistic assessment must account for the human element, not just physics. When we integrate these human factors, the practical limit for conventional human interstellar travel, without significant biological modification or suspended animation, might be closer to 5 to 15 light-years, even with advanced propulsion. This biological limit could potentially be extended through medical advances. If human lifespans were extended to 150 years through anti-aging technologies, or if limited biostasis allowed travelers to skip portions of the journey, the practical range might extend to 20 to 40 light-years. More radical approaches, like mind uploading or full biostasis, would remove biological constraints entirely, but would raise profound questions about whether such journeys still constitute human exploration in any meaningful sense. So, what is our final answer? How far could humans travel in one lifetime? With technologies we could reasonably develop within the next several centuries, without abandoning our biological nature, humans could likely travel 5 to 15 light-years in a single lifetime, enough to reach a handful of nearby stars. With more speculative technologies approaching 50% of light speed, combined with modest life extension, this range might extend to 20 to 30 light-years, encompassing dozens to hundreds of potential stellar destinations. In the most optimistic scenario, with propulsion approaching 99% of light speed and significant life extension or partial biostasis, humans might reach stars up to 40 to 60 light-years away, a sphere encompassing thousands of star systems. Beyond these distances, interstellar travel would require either multi-generational approaches, where those who arrive are descendants of those who departed, or technologies that fundamentally transform what it means to be human? This answer may seem both liberating and constraining. The universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. Yet our biological nature limits our direct exploration to just a tiny bubble within our local stellar neighborhood. Yet even this limited bubble represents an enormous expansion of human presence, from one planet around one star to potentially dozens of star systems. Such expansion would fundamentally transform human civilization and our relationship with the cosmos. Perhaps the most profound insight from this exploration is that the ultimate limits to human interstellar travel may not be technological, but biological and psychological, rooted in what it means to be human. The question itself reveals a fundamental tension between our cosmic aspirations and our terrestrial nature. We are creatures evolved for life on one planet who nonetheless dream of touching the stars. This tension need not be viewed as tragic. Rather, it highlights something extraordinary about human consciousness. We can comprehend distances we may never physically traverse and contemplate timescales far beyond our biological existence. In this sense, human consciousness has already traveled much farther than our bodies ever will. Through our telescopes, our mathematics, our physics, and our imagination, we have already reached the edge of the observable universe, 46 billion light years away. Our most profound journeys may always be those of understanding rather than physical presence. While our bodies may remain within a few dozen light years of Earth, our knowledge and comprehension can span the cosmos. Perhaps this is the ultimate answer to how far humans can travel in one lifetime, physically to the nearest stars, intellectually to the edge of the observable universe, and imaginatively beyond all horizons we can currently envision. As we conclude our journey through the physics, challenges, and possibilities of interstellar travel, perhaps the most valuable insight is not a specific number of light years, but a new perspective on what it means to be human in a vast universe. We are cosmic beings in terrestrial form, conscious stardust contemplating its origins. The very atoms that form our bodies were forged in stellar furnaces billions of years ago, scattered through space by ancient supernova. Our physical limitations in crossing interstellar distances reflect not weakness, but context. We evolved for a specific environment, adapted perfectly for life on one particular world orbiting an ordinary star in the outer reaches of an average galaxy. Yet our consciousness transcends these limitations. We map distant galaxies, calculate the age of the universe, and contemplate journeys across gulfs of space and time that our bodies may never cross. This itself is a kind of cosmic travel. Perhaps the true journey has always been inward as much as outward. The expansion of human understanding, the deepening of our connection to the cosmos, the gradual awakening to our place in the grand tapestry of existence. Whether humans ever physically reach distant stars, we have already journeyed there in other ways. Our instruments capture their light, our mathematics describe their motions, our imagination walks their hypothetical surfaces. The question of how far we might travel contains within it the seeds of wisdom about what we truly are. Creatures balance between limitation and transcendence, between the finite and the infinite, between the physical and the conceptual. As you drift towards sleep tonight, remember that you participate in the cosmos simply by existing. Your consciousness, contemplating these vast distances, performs its own kind of interstellar journey. Join us again soon as we continue to explore the profound mysteries of our universe, one gentle revelation at a time.